All right, welcome to this explainer. Today, we're diving headfirst into what is, without a doubt, computer science's greatest unsolved mystery. I'm talking about the P versus NP problem. And look, right off the bat, I want to say this isn't just some abstract logic puzzle for academics. No, it's a deeply foundational question about the absolute limits of human knowledge and, well, machine computation, too. You see, the whole massive debate really boils down to one deceptively simple question. If an answer is easy to check, is it inherently easy to find? That question is literally the essence of a 50-year-old riddle. It was first cooked up, independently actually, back in 1971 by computer scientists Stephen Cook and Leonid Levin. And you know what's crazy? Despite decades of unbelievable advancements in computing power, it has completely stumped the greatest mathematical minds ever since. Oh, and the stakes? They are incredibly high. Because this problem is just so foundational to math and computer science, the Clay Mathematics Institute actually designated it as one of their Millennium Prize problems. Yep, they are offering a cool $1 million reward to anyone, literally anyone, who can formally prove whether P equals NP or not. So yeah, there is quite literally a massive pile of money riding on this. Okay, so here's our roadmap for today. 1. The $1 million math mystery. 2. Solving versus checking. 3. The NP complete master key. And 4. What if P equals NP? Let's get into it. Section 1. The $1 million math mystery. We throw the word complex around a lot, right? But in computational complexity theory, complex has a very specific, honestly kind of mind-bending meaning. Just imagine you work at a university, and the dean gives you what seems like a straightforward task. You've got 400 student applicants, but only 100 beds in the new dorm. But to complicate things, the dean hands you a list of incompatible students, people who absolutely cannot be paired together. Your job is to pick 100 students out of the 400 without accidentally grouping any of those incompatible pairs. Sounds like something you could just write a quick script for on your laptop, right? Well, actually, wrong. Finding a valid list from scratch by checking every possible combination of 100 students is computationally explosive. To put this in perspective, the total number of ways to choose 100 students from 400 applicants is actually greater than the number of atoms in the known universe. Let that sink in. You literally couldn't build a supercomputer big enough or run it long enough to solve this by brute force. But, and here is where we hit a massive contrast. What if a coworker walks up, hands you a proposed list of 100 students and says, "Hey, I think this works"? Well, you can easily and quickly check that specific list against the dean's list of bad roommates. It would take a computer a tiny fraction of a second to verify if your coworker's list is actually valid. So verifying the answer is incredibly fast, even though finding the answer from scratch seems totally impossible. Which brings us to Section 2, solving versus checking. This massive discrepancy we just talked about brings us to the formal computer science classes at the absolute heart of our explainer. First, we have P, which stands for polynomial time. These are the problems that are easy to solve from scratch in a feasible amount of time. Think of everyday tasks like sorting a list of numbers or, say, finding the shortest path on a GPS map. NP, on the other hand, stands for non-deterministic polynomial time. These are the problems where, if you're given a potential answer, it is extremely easy and fast to verify if that answer is correct. Solving a Sudoku puzzle or that crazy dorm scheduling problem we just looked at falls perfectly into the NP bucket. To make this even more concrete, let's use a really great analogy from our source material. Think of P problems as word problems, where you have to sit down and calculate the answer entirely from scratch. On the flip side, think of NP problems as multiple choice problems. With multiple choice, you don't necessarily have to work it all out from the beginning, right? You can just plug the provided options into the equation and just see what fits. So the absolutely crucial point of the whole P versus NP debate is asking exactly this. Are there any easy multiple choice problems that are not secretly easy word problems? In other words, if every problem whose answer is easy to verify could also be easily solved from scratch, well then, P equals NP. It's essentially asking if human ingenuity just hasn't stumbled upon the right algorithm yet to solve these tricky NP problems quickly. Moving right along to Section 3, the NP complete master key. Now, you might be thinking, okay, to prove this, wouldn't we have to design a new algorithm for literally every single NP problem in existence? Well, amazingly, no. Enter the concept of NP complete. These are mathematically proven to be the absolute hardest problems within the NP class. But they have this almost magical property. As Stephen Cook discovered, an NP-complete problem basically acts as a universal master key. If you can find a fast polynomial time algorithm to solve just one single NP-complete problem, boom, you automatically prove that all NP problems can be solved quickly. How? Well, it works through a concept called a black box reduction. Let's take one of the most famous NP-complete problems, a logic puzzle called 3-SAT. If you, say, build an algorithm that solves 3-SAT super quickly, you can take any other NP problem, like our nightmare university housing issue, translate it into a 3-SAT problem in polynomial time, use your lightning-fast algorithm to solve it, and then just translate the answer back. It's wild. Conquer one NP-complete problem, and you conquer them all instantly. Which leads us perfectly to section 4. What if P equals NP? So, what actually happens if someone finds that master key? I'm telling you, it wouldn't just be some neat academic victory. The utopian outcomes are staggering. I mean, if it's easy to verify a mathematical proof, it suddenly becomes easy for a computer to find that proof from scratch. Computers could literally automate the creative leaps of world-class mathematicians. We could perfectly optimize global logistics, instantly finding the absolute most efficient routes and resource allocations. It would wildly accelerate artificial intelligence, too. Machines could effortlessly generate new physical theories or design crazy complex things like perfectly aerodynamic airplane wings, simply because verifying a good design would mean they could easily compute the best possible design. But, and it's a very big but, there is a catastrophic flip side to this whole utopian vision. Modern cryptography, specifically protocols like RSA, which, by the way, protect your internet banking and all your private digital communications, they rely entirely on the P versus NP divide. You see, RSA assumes that finding the prime factors of massive 200-digit numbers, which is an NP problem, is practically impossible to do from scratch, even though it's super easy to verify if someone just hands you the factors. If P actually equals NP, a single algorithm could factor those massive numbers in minutes. Digital security as we know it would literally vanish overnight. It has definitely been a long road to get here. From Alan Turing introducing the fundamental models of computation way back in 1936 to Cook and Levin formally defining the P versus NP problem in 1971. And today, despite millions of programmers and brilliant mathematicians tackling optimization problems around the globe, the mystery remains completely unsolved. In fact, most complexity theorists today actually believe that P does not equal NP, that some problems are just fundamentally inherently hard to solve, no matter how smart we get. So, the ultimate question remains for us to ponder. Is there a master key out there just waiting to be discovered? One that will unlock a crazy technological utopia while simultaneously destroying all digital security on Earth? Or is the universe simply wired to keep some mysteries and some mathematical problems forever out of our reach? Thanks for joining me on this explainer, and hey, keep questioning the limits of what's possible.